Really appreciate the chance to present here. It was great to end last year with you guys and to start again this year. Super excited about the content today and the subject, which is cybersecurity, in particular zeroing in, if you'll forgive the pun, on some zero trust issues. What KNECTIQ does is we focus on securing data in flight. It's just the area that we identify problems in the marketplace. And what we're going to do today is we're going to talk about what those problems are that we see, how those problems kind of manifest in a number of ways, and then we're going to actually talk about a new solution as well. So first of all, let's talk about what we aren't talking about. We're not talking about needing to do anything with encryption in particular, with the possible exception, quantum computing, which some of you may be familiar with. The encryption algorithms that we have today work great, right? Properly employed, bad actors, people on the internet who are trying to hack into your data are not going to be able to get access because of weak encryption if you're using the right algorithms. The problem is more that encryption works a lot like a lock. And if you think about how a lock works, if I have a key to a lock, I can open it, right? And so it's the same way with encryption. For those of you who aren't deeply involved in cybersecurity, if I have the cryptographic key, I can decrypt the data. That's what it's designed to do, just like a lock opens with a physical key. So let's talk about how we secure data on the internet. So today, I'm going to walk through an example really quick that describes how we secure data for web traffic. You know, like you'll see HTTPS, you'll see that lock on the left side of your bar. That's used for essentially all web pages, but also most machines talking on the web to each other as well. And the way that those systems work, and don't worry, I'm not going to get super into the details if you're not cybersecurity or a software expert, but if you are, you're going to see a lot that you may recognize. The way those systems work is that we have a private key on one end. We use that to negotiate a pair of keys, a symmetric pair. That key then, remember, it works like a lock. I can use that key to encrypt the data before I send it on the internet if I'm a sender, right? So then we send it on the internet to the receiver. The receiver has the same key, so they can decrypt it. And we feel good because if the bad actor gets a copy of that data, they can't decrypt it, right? Because it's, you know, while they might have the bits as they're flying across the internet, they can't decrypt it because they don't have access to this key. So what's the problem? Right. The problem is, first of all, if a bad actor ever obtains a copy of this cryptographic key that's stored at the receiver or the server's end, the bad actor can compromise that data, right? And compromise means, in simple terms, he can either read it or he can change it, right? Reading it's a problem if you're trying to keep that information secret. Changing it is a problem if you're trying to, for example, transfer money. Right? You change which account that's going to, that's a real problem, okay? What that also means is that this key, this cryptographic key at this end, acts as a single point of failure, which is interesting, and we'll come back to that in a minute. It's, but it's not a single point of failure in that it prevents data from being sent or received, but it is a single point of failure in terms of the security system isn't doing what it's designed to do, right? Which is to keep the information safe. But that's not the only problem with the way that we secure data on the internet today. The only reason that the sender trusted this key from the receiver, you know, this PKI, is because it was signed by a certificate authority. And without getting into the details of it, a certificate authority is a means of one of a set of certificate authority companies that exist on the internet in different countries around the world to vouch for the authenticity of this key using math, right? And so what that means then is that the sender knows when it's been signed or vouched for by a certificate authority that that key is trustable. However, the way that works is that the sender has to trust all the certificate authorities on the internet. And what that also means then, unfortunately, is that the private key behind each of those certificate authorities, each of those private keys also acts as another single point of failure, allowing the bad actor to compromise that data while it's in flight. Okay, and it's not even, that's where it stops, right? In addition to the list of certificate authorities that this center trusts, this list is not immutable, right? There are a number of situations where a sender may trust another certificate. For example, your organization may have anti-malware next generation firewalls installed. And they're great tools, right? Because what that means is that anyone who's surfing the internet from within inside of an organization, if they click on a malicious link, that next generation firewall is able to decrypt that data in flight, check it for malware, and if it does contain malware, it's able to filter that content out, right? And keep the network safe. However, the other side of that coin is that if the bad actor gets a hold of that private key that the next generation firewall is maybe using for good and filtering out the malware, that bad actor can again use that private key to compromise the data. Long story short, the way that we secure our data on the internet today is a system that is built on literally hundreds of single points of failure, any one of which failing could cause this data to become compromised. Which is interesting, right? If we think about how we build production systems on the internet today, we have eliminated single points of failure from almost every part of our system. We have redundant power, right? In case one power supply goes, we have backup, right? We have redundant network connections. We have redundant databases. We have load sharing web service and even redundant geographies. So if I'm streaming video from the West Coast and we get the big earthquake and it drops into the ocean, I'm able to fail that streaming over to servers on the East Coast and continue to watch whatever show it is I'm watching without interruption, because we don't believe in having single points of failure anywhere in our production system. Yet, when it comes to how we secure our network communication, when it comes to cybersecurity, we're relying on a 30-year-old system that has not just one single point of failure, but literally hundreds of them. And so what does that mean? What does that mean for users? Okay, so first of all, obviously having hundreds of single points of failure is not secure, right? There are a lot of ways that the system can go wrong. But even beyond that, we also don't even know when the system is failing, because the attack happens outside of our networks. We can't tell who is received and who has decrypted that data. We only know who we meant to send it to. The other side of that coin is that because we don't know where it's being decrypted, we don't even know when the system is being attacked. If we think about this, and this is why I love the topic today of zero trust and cybersecurity, you'll hear a lot about zero trust today. And what zero trust is essentially is saying that only provide data to the person who is authorized to receive it. But when we look at how this system works, can we really call it zero trust when we're actually giving the data to anyone who has obtained any one of these single points of failure, and there are hundreds of them, when we're unable to verify who is decrypting that data, and when we have no ability to detect threats on that system, or at least the threats that are happening outside the network. I would argue that in a very real way, the existing security protocols that we're using to secure the internet are not able to deliver on these promises of zero trust. So that's the problem. And what I'm going to do here in just a second is I'm going to turn around and I'm going to talk about the solution to the problem. And what we're going to do actually, first of all, is talk about that problem from a theoretical point of view. What is it about the existing system that's wrong at a fundamental level, that regardless of how we approach a solution, we need to change in order to address this, okay? But before I jump into that, let me just explain that we are not saying that the systems that are designed thus far, that we're using thus far, don't have a place. The problem isn't that the engineers who created them didn't know what they were doing. It's that they created those solutions 30 years ago, almost, right? And if you think about the internet 30 years ago, this is the time when AOL was sending out CDs saying, welcome to the internet, just use your 56K dial-up connection and get on AOL and hop online, right? These CDs were coming out every time. The population of the internet was doubling literally every single year. And in an environment like that, what does security mean? Right? What you're trying to do in an environment like that is secure a few, relatively speaking, well-known service providers to be able to secure their connection with anonymous new entrants to the internet, all these new people, countries, organizations, whatever it is. We needed a way to enable secure communication in that environment. And so they built the system that I just described, right? And it worked as well as can be expected. Like it's actually not a horrible solution, but it's a security first solution. And then after we have security, then we establish identity. Let me pause for a second and say what I mean by that. If you think about how you log into essentially any site, let's just pick a bank so that we can all feel the excitement of maybe having our finances attacked. If I log into a bank, the first thing I do is I type in the URL or click a link. I look on the left side of the address bar and I look to make sure that we've got that lock there that lets me know that my communication is secured. And only after we have that secure connection do I provide my identity, maybe by a username and a password, right? So that's what I mean by a security first model, right? Is that we're trusting the certificate authority system and the system that I just described to provide security before we share identity and then proprietary information. Our observation is that that solution was appropriate in the 90s when it was mostly unidentified people entering the internet. But today, our most sensitive communication is shared between parties who already know each other. So why not use the knowledge that we have of the other endpoint's identity to establish better security? So when I log into my bank, for example, I know who my bank is, right? My browser, my app, or whatever I'm using can know who my bank is. My bank better know who I am, right? They're holding on to my money. So let's use that identity, that knowledge of identity, to provide better security. Okay, so that's the theoretical underpinnings of what we think a new solution in this environment would need. I'm going to talk really quickly about how our solution works. And I'm going to, as I explain it, ask you to look out for ways that we've eliminated those signal points of failure to provide ultra security, how we're verifying the sender and the receiver for every encryption and decryption operation, and at the same time providing real-time threat detection. So first thing we need to do is identify the endpoints that are communicating. And so what we do is we provision the endpoints a lot like you'd pair your phone to your car. We allow you to simply provision is what we call it. And it's a well understood problem, right? We do it with our phones and our headsets every single day. We aren't using Bluetooth, of course. It's just analogous to that. And we're not using existing systems like HTTPS to secure this communication. We're using rotating crypto, and that may come into play later. Second thing we do is we say who is allowed to talk to whom. In this case, we're going to allow the sender and the receiver to talk to each other. Once we've done that, once we've created our trust network of who's allowed to talk to whom, then we can begin the communication. And that's actually fairly simple to explain. When a sender wants to send data to the receiver, he's going to encrypt it, right? And most application developers are going to have this encryption happen for them automatically, and it's no different with us. What happens behind the scenes, though, is different, because what happens behind the scenes is it causes key DNA to be downloaded to the sending device. That key DNA, just real quick definition of it, is that's just something that allows this device to create a cryptographic key. The cryptographic key is used to encrypt the data, just like we saw in the beginning with how existing systems work, but this is where it gets different. As soon as that data is encrypted, that key is wiped from memory, okay? Doesn't exist anymore. Why? Because we don't need it anymore. No one needs it, right? The data is already encrypted. It's only a target for bad actors at this point. Then the data is sent to the receiver the same way it is today, right? We're not doing anything with how the nodes communicate on the internet. They just talk to each other the same way that they do today. On the receiving end, the reverse process happens, right? Key DNA is in this case downloaded to create the same key, and that key is used to decrypt the data. And then, of course, immediately afterwards, wipe from memory because we don't need it anymore. Okay, the next piece of data, the next communication, whatever it is, phone call, email, chat message, whatever, is going to use entirely different key DNA and therefore an entirely different key. We call this secure because we've eliminated all the stored keys on the certificate authorities, on the receiving end, On the intermediate authorities, if you're into the weeds of how certificate authorities work, we've eliminated all stored keys, so there's literally nothing for the bad actor to steal to try to compromise that data. Okay. What this means is that whereas existing systems have hundreds of single points of failure, we're securing that with having no single points of failure. Whereas existing systems, you don't know who has decrypted the data. Because we're delivering key DNA to every encryptor and decryptor in the network, we are able to verify and log that encryptor and decryptor and create audit logs for the security of our data transmission. And just as with the existing systems, you can't tell when someone has stolen a key that you don't even have access to and is decrypting your data in flight. Because we give you visibility into all of that, when there are unauthorized or imposter nodes attempting to get into your network, we can actually flag that in real time. So every access to every service is verified, secured, and auditable. So zero trust is interesting too, in that because we are verifying and securing every endpoint, we are able to finally deliver on that promise of zero trust, where we are identifying the accessor of the data to the actual provider of that data that they're requesting access to. And that is how our system works.